All right, hello there. Today we're going to do section 5.2, which will let you know how to find eigenvalues. All right, so you remember last time in section 5.1 we ended up with this equation right here, and this was the equation that we solved. We augmented our matrix right here with 0, and we solved for x, but we were always given the eigenvalues. So what we're going to do to find the eigenvalues ourselves is we're going to leave lambda in its place because we don't know what lambda is, and that's going to be called our characteristic equation. Well, not quite, but anyway, there's a couple little things to note right here, and then you'll see what happens. All right, so what we want is we want to find the values of lambda that give you a non-trivial solution, because remember x cannot be a zero vector. So these values of lambda are called the characteristic values or eigenvalues, which you already knew. All right. If lambda is an eigenvalue, then the non-trivial solutions are the eigenvectors, which we kind of already knew. All right. So from the invertible matrix theorem, since ax equals 0 has a non-trivial solution only if the determinant is equal to 0. So you know that this has a non-trivial solution only if the determinant of your matrix right here, this part right there, has a non-trivial, is equal to 0. So that right there is called our characteristic equation. The determinant equal to 0 is called your characteristic equation. And then you get what's called a characteristic polynomial right there. All right, so let's go ahead and see what this is going to do for us down below. And it's going to be, pretty simple. So just follow along. All right, so what we're going to do, remember, what we would usually do last time is we would subtract this with the identity matrix multiplied by the lambda given. Well, this time lambda was not given. So we're just going to leave lambda times 1 in the diagonal right there and put zeros everywhere else. So this gives me this equation, or this matrix, 3 minus lambda, 0, 8, and negative 1 minus lambda. So what I need is for the determinant of this to be equal to 0, because that's going to give me my characteristic equation. So you crisscross, you get 3 minus lambda times negative 1 minus lambda minus nothing equals 0. So this right here is our characteristic equation. Okay? And if you just take the equal 0 part off, then it's your characteristic polynomial. But anyway, there's our characteristic equation. And because it's already pretty much in factored form, I can tell you that my eigenvalues are lambda equals 3 and also lambda equals negative 1. So now we have to go use those and find our eigenspaces or our eigenvectors. All right, so if lambda were equal to 3, so basically we're pretending that lambda equals 3 right here and right here, right? And then we're augmenting it with 0 and then reffing it and all that good stuff. All right, so if lambda is equal to 3, I would get this matrix, 0, 0, 8, and negative 1 minus 3, I would get negative 4. Augment it with 0, all right, ref it, gets me to here, 1, negative 1/2, 0, 0, and all zeros here. So that produces an eigenvector of 1/2 and 1, because x2 is free right there. So my eigenvector is, I'm going to erase this other part so it's not squeezed in so tight right here, is 1/2 and 1. Okay, all right, so let's go finish the other one. So the other eigenvalue, was lambda equals negative 1. So if you do the same thing, if you put negative 1 right here and right here, you get the matrix 4, 0, 0, 8, 0, 0. You ref it, and you end up getting 1, 0, 0, and 0, 0, 0. All right, which gives you an eigenvector of, I guess IV and eigenvalue and eigenvector kind of seem like the same thing. So basically they're asking for the eigenspace, so eigenvector or eigenspace we could say. All right. So that gives me the eigenspace of x2 is free, and x1 is equal to 0. So 0, 1. Okay. All right. So let's do the same thing over here, and for this next one. So we can kind of skip ahead. So you can kind of imagine in your mind that you're subtracting lambda from the diagonal. So you get 10 minus lambda, negative 9, 4, negative 2 minus lambda. You're doing the determinant equal to 0. So when you crisscross and multiply here, you get 10 minus lambda times negative 2 minus lambda, and then minus a negative 36, so plus 36. So in this problem, you cannot just assume that lambda is 10 and lambda is negative 2 because you have the plus 36 over there. So you have to multiply it all out. So when you multiply everything out and simplify it, it comes down to this. Lambda squared minus 8 lambda plus 16 equals 0. So what happens to you is when you factor it, you get lambda minus 4 squared. Okay, so your lambda is equal to 4. So lambda is equal to 4. I don't have a lot of space here, so you would just do the eigenspace or the eigenvector the same as before, as I did in red over there. So when you do that, your eigenspace or your eigenvector is going to turn out to be 1.5 and 1. Okay, so notice what happened here. The multiplicity here I had over in this spot, I had an eigenvalue of 3, and I had an eigenvector for it, eigenvalue of 1, and I had an eigenvector for it. But here, this multiplicity is a multiplicity of 2, but I still only had one eigenvector for it. So that can happen, or it can produce 2 eigenvectors if your multiplicity of your eigenvalue is 2. All right, so let's see a couple more things on this page. So here, we're going to do a 3 by 3 matrix. So here, remember, I would just be subtracting a matrix with lambda across the diagonals. All right, so what that would get me is 1 minus lambda, 2, 1, 0, negative 5 minus lambda in the center, and 0, and have 1, 8, and 1 minus lambda. All right, so I have to do the determinant of this, and I'm stuck, I can't use my calculator for it, so I need the determinant of this equal to 0. All right, so it would be better, since I know I'm doing my determinant, to do what it says in the directions it mentions by cofactor expansion. So the best row or column to use for my expansion would be the center one here, because it has all those zeros. But remember that when you do that, you also have to apply your signs. The top corner is plus, you get minus plus, then you get minus plus minus. So all I really needed to know was the center one right here, because that's what I'm going off of. All right, and then the other piece I'm going to be crossing off is right here. So basically, to do my determinant, I'm going to take negative 5 minus lambda, and I'm going to be multiplying it by the determinant of the other 4 pieces left. And that's a plus spot, and the other zeros basically make everything else go away. So that's going to be 1 minus lambda, 1, 1, and 1 minus lambda. This has to equal 0. All right, so I get negative 5 minus lambda. Then I have 1 minus lambda squared, but then it's minus 1 for that determinant. All right, so when you work everything out, you still have this negative 5 minus lambda. There's no use working that out. And inside here, when you work all this out, it turns out that it simplifies to lambda squared minus 2 lambda. All right, so actually it turns into something that I can factor. So I pull out a lambda. I have negative 5 minus lambda still, and then I have lambda minus 2. So it turns out my eigenvalues are 0, negative 5, and 2. So much in the same way as we did on the last page, you would plug those in into this matrix right here. You'd augment it with 0 and solve it, and you would get your eigenspaces or your eigenvectors. All right, so I'm just going to skip over that part and kind of list them for you here, so you can, if you want to test it out on one of them, you can see that you get it right. So when lambda equals 0, you get negative 1, 0, 1 as your eigenspace or eigenvector. When lambda equals negative 5, you get 2/23, negative 35 over 46, and 1 as your eigenvector. And when lambda equals 2, you get 1, 0, 1. Okay, and they each have a multiplicity of 1, so they're only going to have one vector in them. All right, so then you have a couple more pieces. The invertible matrix theorem, I think it goes down all the way to like Z or something. So anyway, here's S and T, the two different parts. If you have a matrix that's invertible, 0 is not going to be an eigenvalue of your vector, and the determinant is not equal to 0. All right, so one last couple little examples here. So in example 3 is just to remind you that there's an easy way to figure out your eigenvalues if you have an upper or a lower triangular matrix. And so these ones are right across here. And so we know that you have an eigenvalue of 3, you have an eigenvalue of 6, and an eigenvalue of 2. All right, so just to show you, like if you had eigenvalue of 3, just so we're clear, you would basically be doing your matrix A minus 3 times I. So you'd be subtracting 3 off the center green diagonal right there. So you'd get this matrix 0, 2, 3, 0, 3, 10, 0, 0, negative 1. You'd augment it with zeros, and then you would RF that to get your eigenvectors. All right, so in this case, it turns out that when you do that, you get the vector 1, 0, 0. If you do it using 6 instead, you get 2/3, 1, and 0. Remember these eigenvectors, it can be these or any multiple of these. And the last one, lambda equals 2, you get 2, negative 2.5, and 1. Okay, all right. Now, example 4. It says find a characteristic polynomial of this matrix. So again, it's a lower triangular matrix. So there's my eigenvalues right here, and this is just to point out that 3 happens twice. So when I make up my equation, I got lambda minus 2 as one factor. I have lambda minus 3 squared, and then there you can put it a couple different ways, but you could put negative 1 minus lambda as the third parentheses equal to 0. So there's your characteristic equation there, and this has a multiplicity of 1, this one has a multiplicity of 2, and this one has a multiplicity of 1 right there. Okay, so example 5, the multiplicities kind of go with the dimensions for the eigenspaces. So lambda squared there, that would be an eigenvalue of 0. It's going to have a multiplicity of 2. And that means that the dimensions of your eigenspace is 1 or 2. So it can have 1 or 2 vectors in it. All right, so lambda equals 1. It has a multiplicity of 1. And that means that your dimension of your eigenspace is just going to be 1. And the last one, lambda equals 2. That has a multiplicity of 3, and that means that the dimension of your eigenspace, the number of vectors in your eigenspace that describe it, can be 1 or 2 or 3. It can be any of those. All right, and there's last little definition here. It says similarity. So for square matrices A and B, we say that A is similar to B if there is an invertible matrix P such that the inverse of P times A times P equals B, or equivalently A is P times B times the inverse of P. So remember, similarity is not the same as row equivalence. So basically, what similar means is it's basically if one matrix can be brought to the other by a series of reverse steps, like reverse multiplications. All right, and there's your homework down there, and those 4 problems, and shouldn't be too bad. and I'll see you next time.